Hello fellow enthusiasts, welcome back again to my channel. Let's go into today's video and we're gonna come back at the end to wrap it up. Alright, in this video we're gonna be talking about some basic electronics tutorial. Now, we've done videos like this before where we talked about basic electronics, but in this episode we want to go back a little bit and revise some of those things we've learned, and then maybe probably introduce a few more. Now, in this episode, I just want you to look at the basic things you need for every and any electronic tutorial or any electronic project you want to build. The first thing you need is a power supply system. So we'll be building DC or direct current based systems, so we need direct current voltage. And then you need measuring tools or measuring devices. So we'll be using meters, so it could be analog or digital meters, but in our case we'll be using digital meters. And then finally you need project ideas. So some of the things we'll be teaching you, you can apply them to many if not all of these things. So you need a power supply unit. It could be a battery. For instance, we have this 9 volts battery. You can use a 9 volts battery. And now we're not advertising any product for anybody, but just giving you an idea what it could look like. You can use a 9 volts battery. You can also use AAA batteries, AA batteries. You can use any form of battery, any form of power supply to deliver power to the project you're building. And then you can also use units like this. So this is a DC power supply unit. We're gonna unbox this today so we can see how. So this is just Verti. So we're gonna unbox it. It's a 0 to 30 volts power supply unit and 0 to 10 amps current. So let's unbox this, and we'll come back and talk about the measuring tools and then probably some project ideas. What you need, so this is taped around, you need a knife, and then you can just slide through and then cut it open. So let's just cut open this box, cut the tape, and so you can pull this out of the box. So it comes with some manuals you can read to get used to how it works. So let's just get the unit out of the box for now. Alright, it comes with a power cord and some probes to connect to the output supply. So let's do that right away. Alright, so at the back you have the AC connector, so you plug this in and we're gonna find a port or a outlet. We're gonna find an outlet for this, so let's get an extension to plug it in. Alright. Right, haven't plugged it in now. We have to fire it up. So let's adjust our camera. Okay. Now we fired it on. We have to adjust the voltages for the project we want to build. Every project you want to build has a current limit and a voltage limit. In many cases, you just apply the voltage and make sure that the current available from your power supply will be big enough for your project. The project will draw the current it needs from the unit, and I will show you the formula for that. Right now, let's just set the voltage. The project we'll be building will be mostly 5 volts and below, but if it's more, as you have seen, our power supply is capable of delivering up to 30 volts. Actually, this is showing 32 volts, so but we need to get down to 5 volts, so let's put it at 5 volts. You should be fine. Then the current limit, we can set it to up to 10 amps, 10.02. However, we want far less than that, so let's set it to 0. Let's set it to 50, maybe 70 milliamps or 75 milliamps. Let's do 75 milliamps. All right. So that means that the maximum that this circuit can deliver to our project is 75 milliamps. And then when you press the power button on, then the power is delivered to the load. Now no current is being drawn because there's no load connected. So we've set it to 5 volts. We've set it to 75 milliamps. Let's see how much voltage is coming out from this place. Before we do that, let's turn this off. Before we do that, let's introduce the second. So we have one here as a power supply, 2 measuring device, and then 3 project ideas. So let's introduce some of the measuring devices we'll be using. And here they are. We'll be using digital meters. So this one here is a voltage, amperes, and resistance meter. So the current is I, so it's an I. The voltage is V, and resistance is so IR, IVR. So an IVR meter, current, voltage, resistance meter. This one here, it's there's resistance here, so R, there's inductance there, L, there's capacitance. So this is an RLC circuit, an RLC meter, resistance, inductance, and capacitance meter. So for the purpose we're dealing with here, we need the one that has voltage in it. So we will go with the IVR meter. Alright, so we've set our voltage to 5 volts, so we're going to choose appropriate range on our meter. So let's zoom into the camera. Let's zoom a little bit in so we can get clarity. Alright, so we have millivolts, and then we have 20 volts, then we have 200 volts and 1000 volts. So we're going to set this to 20 volts since our range is actually 5 volts, and then we're going to test the output. Right, so let's go back up. I'm just going to move this around, and put the power supply on one more time, and so I'm going to insert. Let's zoom out. Right. So I'm going to insert the probes. So the positive, I'm going to put in the positive, and then the negative. So let's just show the output on. And if I go to the ground, I get about 5 volts. Now if I go to negative, I get about 6.3 volts. Alright, so what we're going to do now is we're going to connect the probes. So the probe is the positive, will go to positive, red will go to red, and we're gonna put the black to black. And then we use these clips to hold it to the probes of the meter. So black to black, you have to remember that, and we have to connect red to red. Right. As you can see, we're getting about. Alright, so this is disconnected. Let's put it back. 6 volts. If I do the ground, so I get practically nothing. So I need to do negative and positive, but the voltage is not reflecting exactly the same. What we have on the power supply is 5 volts, but what we have on our meter is 6.3 volts. This is expected because this power supply is not loaded. When it is loaded and it starts to draw current from the system, the output voltage is normalized. So this is what we call the open circuit voltage. But let's just crank the voltage up and see what happens on the meter. We can get up to 30 volts here, so we don't want to risk that. So we're going to go to 200 on the meter, so that whatever we set, let's try to zoom in a little bit. Okay, so whatever we set the meter whatever we set on the power supply will not blow our meter. So let's crank the voltage up, and I'll just went all the way to 32 volts, and our meter we're getting about 40.9 volts. So let's go down again. Let's put it at 5 volts. All right, so we're done with that. So this is one of the meters we need. We're gonna turn the power supply off. Whenever you're dealing with power supplies, avoid shorting the leads or the output, because when you do, you will draw infinite current from the unit. And when I say infinite, what I mean by that was that, so let's introduce this law right now, the Ohm's law. Ohm's law is V equal to IR. And what we're saying here is that if you short the leads such that R tends towards 0, if R becomes 0, then V, we know that V is not 0. When these two multiply, they will give you V, but V was not 0. So V divided by R is your I. But if R is 0, then V divided by 0 is infinite. So you're going to draw infinite amount of current. But what it actually means in practical terms is that every current available in that system is delivered to your load. Now you don't have a load, it's just the leads connecting from the power supply to your load that you have, and you've shorted it out. When you do that, entire current will flow through the leads, and it could burn the wire. Let me give you a simple circuit here. So if this is my power supply, and I have resistance, obviously you might not really get to 0 ohms, because there will be resistance on the leads. But let's assume you get to that point. So this is R, this is V. The current that will flow through this when this is equal to 0 will be as much as is available. And then the resistance offered by this coil, by this circuit, sorry, if it is 0, then the entire current will flow through it. And then this circuit or this wire better be strong enough to carry that current, otherwise it will heat up and smoke or burn off or something like that. So that's why you have to be very careful not to short the leads, right? So we know that resistance of a conductor is a constant of proportionality between the length and the cross-sectional area, right? So length over A, and that constant of proportionality is rho, so that R is equal to rho L over A, right? So the length divided by the cross-sectional area. So if you have small cross-sectional area, then you have big resistance. If you have big cross sectional area, then you have small resistance, right? Because the R varies inversely with A. Varies inversely with A, right? So if the length is constant, then with a bigger cross-sectional area, you're gonna get small resistance. With small cross-sectional area, you're gonna get a bigger resistance. And so bigger cross-sectional area gives you a smaller resistance. Yes. So in that case, you want to make sure that this circuit, the probes are not so are such that when you shut it, I'm going to shut it, but the power supply is off. So if I shut this way, the entire current flowing in the circuit will flow through this wire back. There's no resistance offered anywhere, and it could burn this wire. It could cause it to smoke and burn. You don't want that to happen. All right, so we're done with that. So let's get the other meter. Let's introduce the other meter. The other meter we have here is the RLC meter, resistance, capacitance, and inductance meter. So this means we can test inductances, we can test capacitances, and obviously we can test resistances. So this kind of meter, the probe gives you the option to plug in the wire for resistance or for capacitance and inductance. So this is common for L and C, common for inductance and capacitance. So I'm going to put the wire there for capacitance and inductance, and then if I want to do capacitance and inductance, the red wire will go into the L and C. If I want to measure resistance, the red wire will go over to the resistance. But that is common, stays in place. Common for both resistance and inductance and capacitance. Then you select the range, power this, fire this on, and select the range and start testing. Alright. So let's look at another meter before we go into circuit ideas. The other meter we're going to look at is another unboxing we're going to do. This unboxing is also for another LC meter, is an inductance capacitance meter. So this is a new meter, so let's unbox it. Right, it has different kinds of probes, and this will be for maybe measuring a component on a PCB, so you can open it and clamp it on the component. So you can clamp this on the component to measure the value, right? So if I want to measure this, for instance, I can clamp it on both ends. The pressure is closing the contact, so that's not what I want to do. But I think I can use it on a circuit board like this. Yeah, so I can clamp it on the probes, yeah, on the terminals to get a value. Alright. So if I want to read the value, as long as there's no power supply to the circuit, I can connect this to it and read the values. Okay, so that's what this probe does. And the wires are short and simple, short and sweet. The reason for that is, remember we talked about the length being a function of the resistance. So the longer the length, of course, the higher the resistance. If the cross-sectional area remains the same and you increase the length, you're going to increase the resistance. And when you increase the resistance in a circuit, that means the current will be lower, right? Higher resistance means lower current if the voltage is the same. So if I keep constant voltage and I increase the resistance, then the current will be lower because the product of the two must be a constant, which is the V. So if my V is 10 and my R is 10, that means my I is 1. If I want to get higher I will reduce my R. If my R becomes 5, then my I, which is drawn from the circuit, becomes 2. If my R becomes 2, then my I drawn from the circuit becomes 5, because at each time the product must be equal to V, which is 10 in that case. If it is 100, if V is 100 and my R is 100, then my I is also 1. If I need to increase my I will reduce by my R by a factor that gives me the value of I that I'm looking for. You understand that? If you have any question, you can put it in the comments. Now let's go into this meter. So this meter is powerful. It has two options to connect power to it. There is this 5 volts power supply here. You can plug in the DC power supply here. There's also 5 volts from USB you can plug in from here. And I think this is a mini USB port. Yeah, because they provide also a mini USB cable. But I think that these days more of this kind of tools should be coming with type C USB, because that is common. But anyways, that's what they've given us. But then there's another option to put battery inside, so you can actually use AA batteries here. So 4 times AA batteries you can use in this thing here. So let's put it the other way around. You can see that AA batteries times 4. You can use that, but we're not going to do that because we have this option with our power supply unit that we just looked at. We just unboxed. You can see this power supply unit has a USB port out. It has 5 volts and 2 amps. So why don't we use that? So what we're going to do is, first of all, to set our volts, we've set it already to 5 volts, and we're going to just plug it in. Let's remove the probes. We don't want to shut it by mistake when we turn the output on. So I'm going to remove this probe, put it aside, and I am going to use the USB. Alright, so this has a switch on the side, so I'm going to fire the switch on, and alright, so this switch here, actually this switch I have here doesn't have any effect on the meter, because it takes power from the USB. This has effect only on the power, on the voltage that goes out on these terminals, right? So whether this is on or off doesn't really matter. Alright, I'm going to put it on and then try to zoom in a little bit to the meter while we perform some tests. So let's take a closer look. So we have the 0, so I think we can zero it out here. So calculating, and then over range it says. So let's connect the probes. So we have these probes. I guess we needed to zoom out a little bit to be able to see the probes. So we're going to connect them black to black as always, and red to red. And then we close the terminal and we can press 0. So we calibrated this so it's all 0. Let's calibrate this as well. So calculating is okay. How about this? Okay, high. Calculating. Okay, it's over range. Let's do that for inductance. Over range. So I believe that is to so we're done here in terms of calibration. So we're gonna check this capacitor out. So this capacitor has a value, as you can see. Let's see if it's clear here. The value is 223k. 223k. That's the value. 223, and then you see K at the end. The K is the tolerance, 223K. So what's the value? We want to figure out the value. We're gonna detect, test it with this meter. But before we do that, let's calculate that. As engineers and technical people that we are, we should be able to figure out what the values are before we use the meter. And so let's do that. So it says it's 223K. Now that K I said is the tolerance. So how to interpret any capacitance value like this ceramic or paper capacitors? The way to interpret it is to know first of all the unit. The unit for all such capacitances are the picofarads, PF. That the unit. So the first digit then is just the digit in the first place and the digit in the second place are all taken into account as whatever numbers they appear as. If it is 10, then it is 10. But the one that is on the third place is not just a unit, but it's a decimal multiplier. So that's times 10 raised to power that value. We're going to call that value x. So to interpret this circuit, this component, then it's 22 times 10 raised to power x, and this x in this case is 3. And the unit is already picofarads, so PF. Then to interpret the actual value is 22 times 10 raised to power 3 times 10. Pico is raised to power minus 12, so times 10 raised to power minus 12. And 3 plus minus 9, 3 plus minus 12 is minus 9. So I was going ahead of myself. So this is times 10 raised to power minus 9. Of course, if you owe 12 and you have 3, you still owe 9, right? So that's a quick way to look at it. You're owing someone 12, but you pay the person 3, you're still owing 9. That's the way to look at it. So in that case, this capacitor then is 22 NF, because raised to power minus 9 is N, nano. Now let's show you how you get to that point, how you get to nano. So the unit of capacitance is the farad, but many times you don't have a full unit, maybe it's a fraction of the unit. So in this case, if I have a unit that is this farad divided by 1000, that unit I can call it millifarad. If I divide this unit again by 1000, I can call it microfarad. If I divide this unit again by another 1000, I can call it nanofarad. If I divide this unit again by 1000, I can call it picofarad. If I divide this unit again by 1000, you can call it femtofarad, and so on and so forth. So millifarad, microfarad. So divided by 1 million is microfarad, divided by 1 billion is nanofarad, and so on and so forth. So this unit tells us that it is 22 nanofarad, but remember there's a tolerance, the K tolerance. K is the tolerance. So that tolerance would tell us the exact value of this capacitor. So it might not be exactly 22, but we're going to find out. So let's bring it back. And for every capacitor, before you test them with your meter, ensure that you short circuit the terminals so that any charge and every charge it has is discharged. Once you do that, then go ahead and connect the terminals. And when we do that, so this is very low value, so we're going to put it in low end. Alright, so the value we're getting is 21.89 nanofarads, but our calculation tells us that it was supposed to be 22. So there is about 0.11 nanofarad missing, which we can attribute to the tolerance, right? So 0.11 or 0.12 can be attributed to the tolerance. Let's just try calculating again and see if we get anything. Calculating is okay. So yeah, so we're close enough, and that's it for this value. Now if you want to test other components like electrolytic capacitors, you can do the same thing, but you have to know the range of electrolytic capacitors are not exactly the same, and the way to test them are not exactly the same. So let's get some capacitors for our testing. Alright, so let's test this one here. First of all, let's look at the value. The value here tells me it's 470 microfarads on 16 volts. So what I'm going to do in this meter then is I'm going to change it to high capacitance. So microfarads, right? Initially I was testing in picofarad range because I was already expecting something in picofarad range. So I tested with low capacitance, but now I'm going to go high capacitance because I'm going to microfarad range. And before I do that, let me just say that I have to also do the same thing here. I have to shut the terminal just in case it was charged. Take any conductor and shut it. And by the way, this one is polarized. You can see the negative sign here, but the other side has no sign. So you just connect the negative to ground, to the black wire, and the positive, the red wire, to the other side, right? And then you're looking at that, it gives you 448. Let's see, let's calibrate it. Alright, so I'm going to discharge it one more time. Make sure I'm getting the accurate value. Alright, so I'm getting 436, but the value written on it was 470. So somehow about 34 microfarads are missing. So this again is attributable to the tolerance of this capacitor. Alright, so that's how you check a capacitor on this. Now we're gonna do inductor. Let's test inductance. Inductor is a very beautiful component. It stores energy just like the capacitance, but differently. Capacitance can keep the energy longer. Inductors will just keep it for a brief moment after the source of power is removed. So now let's switch. So we're gonna go inductance. I'm gonna switch out capacitance because this really I wish that these were linked such that when I change to inductance, the capacitance switch will come up, but it doesn't come up. It just stays down there. And then so I'm testing inductance, but I selected inductance by pushing down, so the top is L, down is C. And then when I do that, I can check high L or low L. This is high L, this is low L. So let me just do let me pretend I don't know what kind of value I'm gonna get. So this is an inductor we got from an AM radio. This is a ferrite core inductor. So I was looking for an inductor to do this tutorial, and I couldn't find one. I was looking for the ferrite rod to do this. I couldn't find one, so I went to AliExpress, and I found about 10 of them for $20. But I just needed one to do the experiment, and so I didn't want to spend $20 for that. So I opted to just buy one, but I couldn't find one easily. What I did was I went to a local store, a Salvation Army store, and I found this little radio. This radio, it's an AM FM radio. So the radio really works fine. And this radio goes for $2. So it was sold as is, and I got it for $2. Then when I opened it up, I took this inductor, this ferrite rod, and then the FM radio still works. And then of course it has battery pack, has two speakers, right? It has the volume control and the switch, and it has the variable capacitor and also the knob for it. So all this for $2. So if you're an enthusiast, you might be looking at your thrift stores, local thrift stores, for hunts like this. So I call it treasure hunting. Right. So I'm gonna connect this and then check. So and I'm seeing that the value is 664 microhenry. 664.1 microhenry. And then let's check the other one because there are two of them here. And the other one tells me it's 15.46 microhenry. So is any of them high or low? Let's try. Yeah. So it's better the range we use, because here you have to divide by 1,000 again, 1, 2, 3 to get 15 microhenry, which is fine. Or if I go to low, I just get it at 15.45 microhenry. Now this is affected by the presence of a conductor or a medium as my hand comes closer, especially if I use a metal object closer. It will change the value of the inductance. And if I use a magnet, I have this neodymium magnet, it will even change it more. I'm going to be very slow in coming close because it might induce a lot of voltage, as you can see. So the value changed drastically from 15 to 12. If I take it off, yeah, it goes back to 16. It's going to drop because the voltage induced is going to be transient and it will gradually wear away. Right, so this is 12 or 15, sorry. I'm going to try the other one one more time and do that magnet thing. Right, I've switched it out. I'm getting my 680 something again because of the residual magnetism. But I'm going to bring another magnet close, the same magnet closer, and the value is dropping to 400 plus. So you have to be very careful when you do this, because I don't know how much voltage is being induced into this thing. I'm saying voltage because, you know, when a magnet moves around a coil, it induces voltage. And when voltage moves around a coil, it will create magnetism and back, you know, and so on and so forth. So we've tested this. Now the next thing we're going to look at is circuit ideas. So I'm going to put this away. Power supply, shut it off. When you're not using the power supply, just turn it off. There's no point wasting the energy, right? You have to be energy conscious. Now let us look at some circuit ideas. So what are the circuit ideas? We've looked at the power supply unit. We've looked at the measuring tools, and we've looked at some components, inductors and capacitors. Now let's look at some circuit ideas. What circuit can we build with inductors and capacitors? This is an inductor. This is a capacitor. One thing come to mind right away is a resonance circuit. If you're familiar with this kind of terrain, it's a resonance circuit. So there's what we call parallel and series resonance. So if I connect these two components in series, I will create what we call series resonance. And if I connect them in parallel, I will create what is called parallel resonance, right? But what is resonance? Resonance is the point where you have the highest energy in this circuit, or when there's 0 volt, 0 ohms in this system. And how do we get to the point where we have 0 ohms? And it is a system where the inductance, as a result of this inductor, the reactance as a result of this inductor, and the reactance as a result of the capacitor, they have equal value, or they have opposite polarities. So if you get to that point where they have equal value and opposite polarities, then you have resonance, right? So there's no resistance offered to the current flowing through this system. And so how you calculate inductance then? The reactance. How you calculate the reactance? We're going to look at it quickly. So the reactance for an inductor, so inductive reactance, is the same thing as omega L, and the capacitive reactance is the same thing as omega C, 1 over omega C. So inductive reactance, capacitive reactance, and we say that they have to be equal and have opposite signs. So at resonance then, XL is equal to negative XC. It can be anywhere around, so it can be XC is equal to negative XL. And now we already say that XL is omega L and XC is 1 over omega C. What is omega? Omega is the angular frequency, so 2 pi f, right? That is omega, such that XL then is equal to 2 pi FL. In that same vein then, XC is equal to 1 over 2 pi FC. Alright. Then I will not solve all the equation, but you can solve it yourself. So 2 pi FL is equal to minus 1 over 2 pi FC. When you solve this equation and you make F the subject of the formula, then you will get that F is equal to 1 over 2 pi square root of LC. Now it is easy to figure out why this is the case, because you have F here and F here. That's 2 F's. You have 2 pi here and 2 pi here. That's 2 pi's, right? So, and you have 1 L and 1 C. If you're making F the subject of the formula, because you have 2 F's, a product of each other, we have 2 F's and you get only 1 F. So F squared originally will be F squared, but you're taking square root of that. So when you solve this, you're going to get that F is equal to 2 pi, 1 over 2 pi over LC. Now remember, this is just, this negative sign just tells you that they're equal and opposite. They're going in opposite direction. Okay. So then this F is called the fundamental frequency. And now the reason we're going to do this first is because when we did our 1 transistor FM transmitter, 1 transistor FM receiver, we got so many comments. It has thousands of views, and people commented, and many of the questions were, how did you get the value of L? How did you get the value of C? What was the value of L? What was the value of C? And sometimes maybe an oversight, we didn't state the component, or maybe we stated it in the circuit diagram, but people just didn't catch it when the video was showing because they weren't emphasized. The reason that the components weren't emphasized in our transmitters and receivers were because they are not as important as understanding the principles. And that's why I'm taking this time to go back and introduce that as a circuit idea and help you understand why we did what we did. So let's just do a little exercise here. So in a previous video, we've shown how to build a transmitter, and we say that you need an oscillator. And how to build an oscillator is to build an amplifier first of all, and take a component of the output and feed it back into the input circuit. When you do that, you have built an amplifier. You have built an oscillator, sorry. But then every oscillator requires a resonance circuit, and resonance circuit, like we've just seen, is an inductor and a capacitor. So here we have an inductor, here we have a capacitor. So we need a parallel resonance. Alright. And then we just took a portion of that to the emitter circuit, right? And then we can have our antenna somewhere here to radiate the energy. And then you can control the amplitude of the output by this here. And by the way, I think if you want to build a good a simple AM transmitter, I want you to build the FM transmitters we used to build, and make sure that the resonance circuit oscillates in the range of the AM band, which is 54 kilohertz, or I think it's 540 kilohertz, sorry, to 1.72 megahertz. In this range, when you do that and you modulate the signal from the emitter, so I would suggest using a variable resistor here. I know I'm segueing here. I just have your audio in here. When you do this, because the value of this it provides temperature stability. However, if you can just modulate it slightly, you can actually modulate the amplitude, and therefore creating an amplitude modulated transmitter. But this is a discussion for another day. Now you just have to bias this transistor. Then normally we use 2K to resist here, 2K to bias that. If you're operating from 1 volt to say 1.5 volts to 3 volts, we normally use 2K to resistor. If you're using higher voltage, then change the value of this or use a resistor to drop the voltage. And then we have a capacitor here, and I think that's it. You can now feed your input here for FM transmitter. So when you modulate the base, you are modulating the frequency. When you modulate the emitter, you're modulating the amplitude. So you can try this out. Now this is a typical TV transmitter. You can actually use this simple circuit to build a TV transmitter, where you have your audio in here, your audio, your video in here, video here. Sorry, for FM transmitters, TV transmitters, you want to do your audio in from the base. So you have the FM frequency for the audio, and then you use here. If you're building a TV transmitter, you want to feed your video here for TV transmitters. Feed your video in here for. But if you want to do AM transmitter, then feed your audio in here. Alright, we can do a separate video for this, but just to give you circuit ideas what you can do. So now we have the resistance, you have the capacitance, inductance, transistors. We're going to be looking at transistors in some. We have some videos on this, so look at our channel, find the videos on transistors. But this is a simple transmitter we built here. Obviously it is not complete. You need to have a filtering capacitor here, as close to the circuit as possible from the power supply. And then how many components do we have here? 1 2 3 4 5 6 1 2 3 4 5 6 7 8 9, about 9 components. You've built yourself a transmitter. Build this and let us know. So when we build things like this, and then we call this L and we call this C, and people are asking us, what value is this, what value is that? And sometimes we give you the value of this inductor by the number of turns. And now it is difficult to put everything in one tutorial. That's why we're doing these basics. So go to our website, hackerworld.com. That's a calculator. Also on the screen you can see the logo Hacker World Unlimited. So that's the domain is Hacker World. Go to hackerworld.com and you will see a calculator. The calculator helps you to figure out these things. So if you have the F, which I believe you should, if you're transmitting on any range, make sure it is legal in your country. But let's just look at this. So 54 times 10 kilohertz, so 540 kilohertz to 170 times 10, so 1.7 megahertz for AM band, and for FM is 88 megahertz to 108 megahertz. So you already know the range you want to transmit in. So your F is known. In this case, your F is a range. F is a range. So F low to F high. And so you need to find the values that will cover that range. So you can take a fixed L and find a variable C, or you can take a fixed C and find a variable L, or you can have both variable. But if you want to target a particular frequency, choose values that will give you what you're looking for. What do I mean by that? Remember that F is a function, is an inverse function of the square root of L and C, right? So it's an inverse function of this. So 2 pi is a constant. I'm just going to put it for the sake of it. 2 pi is a constant. Now, if I use a particular L and C to get what I'm looking for, you don't have to have the exact values. You can use what you have to get what you're looking for. Go to that website, look for that Omni calculator on our website, and you plug in. If you want to make the turns yourself, it will tell you how many turns you need to make certain inductors. Or if you already know the inductance value, it will tell you the capacitance value you need to get a particular frequency. So do that. But let's just do some exercise here. So if my F is 100 megahertz, and I'm using this loosely, don't take it as the exact solution, but I'm using this loosely. I'm using it loosely. So if what I use for my L and my C, if I use for my L 100 and my C 1, such that I got 100, what you need to do is you can figure out what you have. If you have 1 here, then get 100 over there. If you have 2 here, then get 50 over there. If you have 50 here, then get 2 over there. If you have 4 over here, then get 25 over there. If you have 25 here, then get 4 over there. If you have 20 here, then get 5 over there. If you have 5 here, then get 20 over there, and so on and so forth. Because you want that at the end of the day, that inverse function gives you the same frequency that you're looking for. So after now, you will not be asking people, what value of inductance did you use, or what value of capacitance did you use. You can pick it from their system, or you can use the one you have. If you're like some of us that keep some components around, you can just scavenge through your treasure hunt and you find something that you're looking for. Like this radio is really doing nothing for me. Yeah, it's really doing nothing for me. So I can open it up and take whatever I want from inside. I can take the antenna. If I want to build a transmitter and I need this type of antenna, I can take the antenna. I can take the variable capacitor here that is used for this, because I know already covers the range. I can take the speakers. I can take the battery pack. Like there's so many options available for you. I can take the switch. There are 2 switches here. They can take for something else, right? There's a switch here to select between AM and FM, and then there's a switch here to turn it on. Now we know that AM band will not work now because we've scavenged the inductor, so we'll get nothing on the AM band, but we can get something on the FM band. So we'll get nothing on the AM band. All right. And you know the reason already, because you need resonance, and the resonance occurs when both components are available, when the L and the C are available. If they're not available, you don't get resonance. So we've scavenged the inductor. The capacitor is still there, so we need to put it back before it can work. All right. So that is that here. So we're done with that. So this is a good idea. I want you to build a transmitter or a receiver. Both of them will work on the same principle of resonance, right? So there's another inductor I want us to look at. Very, very small inductor, but I think the value is pretty high, and so let's try to locate that component. Very tiny inductor, and the value was influenced, I believe strongly, by the presence of a ferrite core. So we have some inductors here. We're going to test them out. And we have some capacitors here, also variable capacitor. We're going to test out. And so let me look for another. There's a tiny inductor, very small inductor, that I want us to look at if we can find that inductor. And we can find it. That's the inductor. There's another inductor here. There's another paper capacitor here. So let's take a look at those. So that means we have to reintroduce our meter. Alright, fire that up. And let's test the inductor first. So this tiny inductor, what do you think the value will be? Now before we test it, if you look at it, you see it has just a few turns of wire on it, right? And then we have this one here that obviously has more wires if you compare both of them. It has a lot more wires. So let's test the inductance. We clamp this here. We clamp that down there. And we get 0. The value is 0. We get nothing. Right. So let's take it off. And you know it's trying to read something, because when the moment you connect it, the value flashes on the screen, but it gets nothing. Alright, so let's connect this one here. And right now we're getting about 41.21.18 microhenry. Let's go high. I reached nothing. Out of range. Oh, sorry. Yeah. So it's about 40 millihenry. So divide by 1,000 is like 40 microhenry. So let's go low, because we know it's already lower, and the actual value is 41 point something, right? So now, why does this give us so much value when this one here with a lot of wire give us nothing? I think it's because of the presence of the ferrite core in this one. So if I put this ferrite core inside, maybe I'll get a different value. No, I don't get any reading. So I don't get any reading from this. Alright. So I don't get any reading out of this one here. So the value is really low for the range of this inductor. Let me try this other inductor here. This one is a range. So this one is a range here. I'm gonna try to find out what the value is. So it has 5 terminals, but the connection is only on 2, and this ranges from, I think, 0.7 to 1.6 if I'm not mistaken. So let me just connect this and see what value I get. Alright, so this is not giving me any reading, so let's try the other probe, and we can clamp it on the terminal directly. And since this is variable, we can try to vary it. So we need to get let's see if we can get anything out of this. So I'm gonna try to vary it. You're right, I get nothing from this inductor. Alright, so this is probably out of range for this. So let's try the next one here. Alright, so this, you don't see the reading here. So this seems to have some values as you adjust it. So it's just low, it's 0.0 something. It's low to come into range. So we need a different meter that is more sensitive than what we have. But this is variable. As you're changing the position of the ferrite core, the value is changing. Yeah, the value is changing by varying that. So I'm going to try the first one again, and I've seen I need to adjust it and see the values. No. All right, so what we're learning from here is that you need the right equipment, and it must be of the right range to read the component. All right, so we're gonna keep this one down. So when you buy these components, make sure you get the right range. When you buy the equipment, so the measuring tools, make sure they have the right range to test what you want to test. Now we're gonna test variable capacitor. Let's see if we can get something out of that. So we go capacitance, and let's see. So this one is 26. No, this is trying to, I'm going to use a different probe because I don't want to crush the terminals. So I'm just going to clamp to one of them, and then get the other probe, and clamp on the second terminal. Yeah, so this is about 20 picofarads. So I'm going to try to vary it and see the value. All right, so we need a better adjuster. Let's find a different one. Okay. Alright, as I'm adjusting this, the value of the capacitor is changing. Now of course my hand is influencing this value, so I have to have a beta clamp to hold it and then try to adjust it. But you can see as I adjust it, the value reading on that is changing. And this is how you can adjust the frequency of your circuit. So if I clamp it and leave it, so I'm thinking it's about 20 picofarads. So I have 20 picofarads and I have 41. So let's focus on this too. So so 20 picofarads and 41 microhenry. So what is the resonant frequency that I'm gonna get from this? So if you apply the formula we just learned, F is equal to 1/2 pi square root of LC, or you just go to hackerworld.com and plug this in and you find out the frequency that this will resonate at. So if you use these two components, that is this one here and that one there, what will you get? Let's see if we can do that live. Let's see if we can add this demonstration and then we can call it a day. So let's go to a website. I'm gonna go to HackerWorld. Hackerworld.com. I'm gonna show you the screen once I get there, because I had to add it in the broadcast. It wasn't part of the plan, but now we are there, so we can just show that night calculator, and let's add the screen. Right, add a window. All right, and we're gonna find that all right, so that's not what we want. We want to add desktop. I think we want to add desktop. All right, so the tool is not responding. This card, so this screen, is it scene or screen? Image display capture, game window capture. I think window capture should be fine, but we're not seeing that window. All right, I'm gonna do that one more time and see. Media display capture. All right, so I think we need to add a browser instead. So why don't we use a browser? Let's use a browser, and we're gonna add HackerWorld. Sorry about that. We're just trying to figure out the browser we need here is HackerWorld Unlimited Night Calculator. All right, let's see if it works. All right. All right, so it's showing right now. So let's just hope that this works for everybody. It's so tiny. Now it's upside down. What is going on? It's upside down. Let's flip that, transform that upside down, transform it vertically. All right, and let's do the calculation. Let's get the window up. All right, so we need to calculate the frequency. Alright, we need to calculate the frequency, and we have the inductance. Inductance is 41 so 41 microhenry, so it's going to be 41 times 1 million, so 41 1 8. All right, and then the frequency is going to be in picofarad as well, so 20.16. And when we do that, the frequency is around 5.5 megahertz. So when you build this system the way we've designed it, when you use these components, the inductor and the capacitance, your system will be resonating at around 5.5 megahertz. But this will be maybe in the shortwave band or something else. So what we want to do is we want to operate in the AM band. So what do? So we have an inductor already, and let's calculate the capacitance. So we want to calculate capacitance. So we have an inductance value already, and we just need a frequency. So the frequency is 540, which is 0.54 megahertz. So 540 kilohertz. That means you need 2 nanofarads. So if you get a 2 nanofarads capacitor and you use it together with this inductor, you can operate in the AM range. So we're going to try to build an AM radio using this tiny component with the 2 nanofarad capacitor. Alright, so let's try the other end of the spectrum, which is 1.7 megahertz. So you need a 20 nanofarads. So 20 nanofarads, and 20 nanofarads will get you to 0.2 nanofarads. 0.2 nanofarads. 0.2 nanofarads will get you to 1.7 megahertz. So let's summarize. So I'm gonna take off the screen right now, and alright. So we found out that with a 2 nanofarad we can get 54 kilohertz, 540 kilohertz, sorry. But with 0.2 nanofarads we can get up to 1.7 megahertz. So we're saying find a capacitor that is in this range, and you can build an AM receiver or even transmitter with this component here. So and we're gonna do that. We'll have a lot of these components around. We have 2 nanofarads or 0.2 nanofarads around. We can use that, and this 0.2 nanofarads is the same as, if you multiply by 1,000, it's same as 200 picofarads. So you can find that. So this is the same thing as 200 picofarads, right? So we can find 200 picofarads. So that will be actually 200 written on it. That will be 200 or 201, actually 201. Sorry, it's going to be written 201 on it. 201. The reason we say it's 201 is because, as we said earlier, the third digit is the decimal multiplier. So we're going to need 201. So 201 is the same thing as 20 times 10 raised to the power 1 times 10 raised to the power minus 12. So this is the same thing as 20 times 10 raised to the power minus 11. That's the final value. But this one here, you can shift 1 0 and call it 200, because the nearest unit to make it beautiful is PF. So you need 201. So we can 201 for 0.2 nanofarads, and then we need 2 nanofarads. 2 nanofarads, let's see what 2 nanofarads looks like, is 202 times 10 raised to the power minus 12. So that is 202 or 20 times 10 raised to the power minus 10. So if you now go one digit to the left, this becomes minus 9. So this becomes 2 NF. So we need 2 N. We need 2 NF. I was confusing both of them. So points 2 and 2. So you know 0.2 and then you need 2. Alright, so let's see what we have here. This value here is 104. So 104, what's the value of 104? Let's do the calculation for 104. 104 times 10 raised to the power minus 12 is the same thing as 10 times 10 raised to the power minus 8. And now to get this to read actually minus something that is within what we've discussed before, we talked about MF, micro F, so millifarad, microfarad, nanofarad, picofarad. So nano is minus 9, minus 12, minus 15, minus 6, minus 3. So to make it look like this, so it's nanofarad, we have to, so minus 9, so we have to shift this by one digit, so it's going to be 100 nanofarads. So let's see what meter tells us about that. Alright, so this is the range here it's way off. So let's see, 104 is giving us 30 something. So I think my review of this tool right now is that it is not very accurate. That's my initial feedback for this tool. It's not very accurate, because right now it's giving us 36 nanofarads, but that's not the case. Alright, so this value is not accurate, so I'm just going to verify and maybe I need to provide a feedback to the vendor of this tool. Yeah, 104 should be 100 nanofarads, but I'm reading 36. Okay, so there's something wrong. It's either the part is already bad, because I pulled it from a circuit, so it's either the part was already bad or something wrong with the components. So I'm going to try another value before I give my final verdict. Let me try another value before I give my final verdict. So we have a bunch of capacitors. So let's find another one. The electrolytic capacitors, the values were closer to what the meter was giving, but I don't I don't think this meter was accurate or even near accurate in this one. So let's look at other ones, and this is where we're gonna call it a day. Right, I have 104, 221. So I have two 221s and one 104. So we're gonna start with 104. All right, so this is still giving me 26. So not a very good feedback for this vendor. Let me try see if I can reset this. All right, still gives me 26, 27, and then 221. This should give me like 220 picofarads. 221 should be 220 picofarads. Closer. Okay. Let's try the last one. Just give me 220 picofarads. No, so they're all wide. The ranges are all wide, and this could be why when you build some circuit, if it is true that these components are giving this reading, this could be why when you build some circuits, especially AM or FM radios or any RF radio, you are not getting the expected result because the components have wide ranging values. I have two in parallel, so the value should increase from 220 to 440, but I'm getting 350 something. And if I put them in series, the value should drop by about half. Let's see what we're getting. Not really. 220, half of 220 should be 110. All right, so these components are not exactly. I'm gonna try to get standard components, golden components to test this out. 104 should give me 100, but it doesn't give me 100. All right. Now we got some secret ideas, but we have to figure out. Go to the internet and find out what the value of 221 is. 221, because we're saying from calculation that 221 should be 2 times 10 raised to the power minus 11, which is the same thing as 220 picofarads. Confirm that on the internet. And also that 104 should be the same thing as 10 times 10 raised to the power minus 8, which is 100 nanofarad. Confirm this on the internet, and then I'll have to give a feedback to the vendor of this component to show that this is not accurate. The reading is not accurate, or maybe the components are not accurate. Maybe the meter is good and the components are not. You have to figure that out, and we're gonna do all those offline. All right, it's been quite an introduction today. So right, how do we sign off today? All right. We just want to thank you for sticking around to the end. Please do like, share, subscribe, comment, and we have to see you in the next one. All right, like, share, comment, and we hope to see you in the next one. All right, thank you so much. We really appreciate those of you that keep coming back. So again, thank you very much. See you in the next one. Don't forget to like, share, subscribe. Stay enthused and keep doing what you're doing. All right.